Finishing up, we are talking about caves in the last video. Let's go back over that a little bit. Got a little different picture here to look at. And basically, this happens in, like I said, they're called karst topographies from an area of Yugoslavia called Karst region, and that characterize this. But it's also found, like I said, in Texas and Kentucky in the United States, very common. All right, and basically you have here you have a stream coming through, water coming down through the limestone, and as it does, you have very thin soil. As it gets in the rocks, it starts being mildly acidic because it has a carbonic acid, carbon dioxide plus water makes carbonic acid, and gradually, as the water runs through these, it tends to dissolve and eat away a little bit at the limestone over time. Okay. Now, as the stream gets deeper, that drains this out, and so now you have a lot of emptier spaces out here, okay? And eventually you have this big empty areas up here, which makes these large caverns, all right? Now, if these are to collapse, whoops, sorry, I'll make the whole thing collapse, all right? All right, if we were to collapse down, then this would leave sinkholes at the surface, okay? Sometimes there'd be kind of sinkholes where it washed down and eroded away a lot of the limestone there, all right? You see where some little ones have already sunk in, and eventually you could have larger ones if the whole cave collapsed. As once the caves become empty, then now this water is dissolving limestone. As it drips off here, would leave formations on the top, which are the stalactites, which are hanging on tight, and the stalagmite down here, building up where it lands and leaves deposits behind. But all those different cave formation stuff that you can see here. All right. Other places this occurs is in China. These are places where most of the areas have dissolved away. You just have these big areas that are left after other areas collapsed around it and so forth in China, and very unique kind of looking. And in Kentucky, this is an example of a karst landscape where a lot of things have collapsed over time. And you can kind of see there's low spots, whoops, sorry, kind of a lot of low spots here where things have collapsed, which gives it kind of a hilly look, but really that's because of so many of these low spots where the limestone below it has actually collapsed. Now, besides groundwater and aquifers shaping the landscape a lot, we also have a lot of work is done by streams and rivers. Okay, and we're going to talk about that. We're not going to get into glaciers too much because it's not such a big deal here. If we were farther up north, I was fortunate to go to Alaska, and they had some really cool glaciers up there, and it really got me excited about it, but it's really not as big a deal for us here. So I'm going to concentrate more on what we have. So we're going to talk about streams and rivers more. But just know glaciers are an important part. Okay, but streams and rivers are probably one of the biggest ones. They are important as eroders or removers, if you will, of sediments, and they're also important because they deposit new sediments. So they get rid of things in some places, they deposit or dump things somewhere else. Now, how much they erode or how much they deposit has a lot to do with the stream flow, and there's several things that affect the flow of a stream. Okay. Factors that affect it. The first one is the gradient of the stream. All right, and basically, how steep is it? Generally speaking, near the headwaters or where the water originates, usually up in the mountains or higher elevations, and so they tend to be steeper. And so you tend to have little streams tend to be faster flowing. They don't have to be. They can be very shallow also. Okay, for example, if this kind of flattened out up here, you might have some small, slow streams going up here that eventually pick up speed when they start going down elevation. But since the headwaters are going to be at the higher elevation, it's going to empty down at the lower elevation. Generally, they're going to be faster and steeper at the top. Okay, very often around mountains. Okay, as they travel farther through, then they may get to where it's flatter. Okay, if you get down the Mississippi River, for example, and look around the sides, it's pretty flat. Okay, but gradually it does go downhill, and so it heads this direction. But since it is flatter, it tends to meander a little bit more because here it's going so fast, it's just plunging downhill and doesn't have time. It's pretty straight. As they get down here, they tend to meander a bit more. Okay, and so generally the closer you are to the headwaters, it tends to be steeper. As you get closer to the mouth or where it empties into an ocean, lake, whatever, it tends to be flatter as a general rule. All right, now how much discharge or how much water can a stream carry, and how would you calculate that? Well, basically it has to do with a cross-sectional area. Okay, So it's equal to the cross-sectional area. I'm just going to put CS for cross-sectional area times the average stream speed. Okay. Obviously, the bigger, if you had a stream like this and you had one that had twice as much area, obviously this one's going to have more water because there's more water going by if they're moving at the same speed. Now, if this one was moving twice as fast, though, even though it doesn't have as much area, it has twice as much water coming by in the same amount of time, so it might have the same discharge, okay? So just because it's a bigger cross-sectional area, if you do a line through and look at the cross-section of the water coming down, it depends on how much cross-sectional area there is, because that's the volume of water coming down, but it also depends on how fast the water is moving through there. Okay, and so it's basically those two things. Now, a couple things about the shape then that can affect it. In general, the rounded, deeper channels are going to have less water near, most of the water is going to be away from the edges. Okay, on the other hand, if you have a wide, shallow, all of the water is close to the edge, and where the edge is, you're going to have friction, and so the friction is going to slow it down. So in this example, the fastest water is going to be here, so these rounded, deeper stream beds tend to have faster water overall, the average speed. Notice we said the average speed because it's going to be going slower around the edges, but it's probably going to be faster up here. On this one, almost all the water is near the edge and therefore subject to friction, and therefore it's not going to have as fast a current, generally speaking. Now keep in mind the Mississippi River is fairly flat, but it's also fairly deep, and so most of it is not having much friction along the edges, and so it's still going to be moving fairly fast even though it is a flat stream bed. But in general, the more water that's away from the edge, which is going to be these deep round ones, they're going to be going faster in the middle, whereas the closer it is to the edge, you have more friction, and therefore it's going to slow. Now, it can also depend on what kind of materials are there. Alright, so if we tend to be flatter, the land is flatter, and it's going smoother, you tend to we'll have laminar flow. Laminar flow, the only particles still suspended are like little mud, sand, silt particles, and so forth. Okay, so it's generally tends to be slower flow, and it's just carrying those small particles. All right. On the other hand, once it gets turbulent, usually turbulent tends to be on areas that are steeper. Okay, the elevation's increasing. Also, you have the rough things on the bottom here cause more turbulence, so water goes up and down. The extreme example of this would be whitewater rapids. Okay, this water, since it is going faster and it's got a lot more turbulent flow, can pick up and even spin some of these rocks along the surface, and bigger rocks and gravel and sand and things like that, and they're going to carry more of that stuff along. All right, whereas here, if you had that kind of stuff, it would have settled out a long time ago, and only the smaller particles can be carried in the laminar flow. All right, so the turbulent flow is going to do a lot more of that and carry stuff along with it. And this is what's responsible to the nice rounded river rocks. My wife always likes those. Wish we had some big ones that we could put in our yard, but it's just rolling across the bottom, wears them down and smooths them off and makes them rounded like that. All right. Now, the last thing is the channel geometry, or the shape of the stream. Okay. If you have a straight river, it's going to be fairly consistent. But if you have one that's got bends in it, okay, generally speaking, when it comes in here, the fastest water is going to be over here on the outside curve of it. Okay, and also because of inertia, it's going this direction. It wants to keep going this direction, so until it hits the bank over here. And so we have a cut bank where it starts eroding away over here, and occasionally this will fall in as it eats the bottom out. The weight of the dirt above it falls in. Eventually you may have this tree just fall over because too many of its roots have been washed away, and it will just fall in. Okay, now as it moves back this direction, the speed's kind of back toward the middle, but as you get where the curves again, once again, the fastest speed is going to be on these cut banks. Okay, and once again, it's going to tear this up. Now, the slower is going to be here, around this corner, and around this corner. They're going to be slower. So this tends to be where you get sediments deposited because it's slower, so things settle out of it more. So you have these bars or sandbars, point bar it calls them here, but whatever, sandbars on the inside of the curve, on the outside of the curve, where it tends to have a lot of energy and it tends to erode away a lot of sediments. So basically, we said the streams can be responsible for erosion and transport of sediments. They pick them up, wear them off. Some is chemical. There could be chemicals dissolved in the water that wears away at the rocks and so forth, that eat at the rocks. But more likely, you tend to get the hydraulic action, the force of the running water actually hitting these things. I talked about rubbing on these rocks and kind of wearing away. In fact, there are some places you can see where if there's sediments in the water, they act almost like sandpaper and do this, okay? And that would be considered abrasion, where it's not just the water moving, it's actually the sediments in the water, and they're really wearing away, and I can kind of like liquid sandpaper, just wearing them all nice and smooth and rounded. This is an example in a rocky riverbed where something about it causes it to start swirling around, and the basically the sediments and stuff like that cause it, as it swirled around, just basically drilled a hole down into the rock. Now, if you have a hard layer of rock but there's soft sediments out beside it, the soft sediments get worn away, but that hard layer stays there, and so now you have like a shelf, and it drops off of there, and then of course that's what creates the spectacular waterfalls, and that's just differences in the materials that are being eroded away that causes that. Now, so once again, you have early stages tend to be faster, going from higher elevations. They tend to have more what we call a V-shaped. If you were to take a cross-section of the channel, it would be a V-shaped channel. Okay, as they get older, you can't see it as much here, but they tend to have more of a U-shape. Okay, the V-shaped stream valleys, we call them stream valleys up here. The stream valley tends to be very sharp. You can see on the waterfalls we had a minute ago, very steep sides with a creek down at the bottom. You know, here's your creek at the bottom. You got very steep sides, mountains going up on either side. That's more of the stream valley, and the actual channel of the water going through is more of a V shape down there. Okay, you tend to have more likely to have waterfalls. You tend to have more rapid flow, and it's at the higher elevations. As you get to the lower, it tends to be less direct. It tends to meander back and forth because there's not as much elevation. Okay, the example down here of an old age river here where it's going back and forth. Occasionally, water on these curves will even take little shortcuts, and so like here it cut a shortcut and it leaves this little part over here. It's called Oxbow Lake. Okay, and that's basically what used to be one of the loops here, but it took a shortcut and this got stranded out here all by itself. So now you just have this little lake that's kind of out there on its own. Okay, and that's more of a sign of a the floodplain or older stage river where it's got more of a U-shaped river. It meanders back and forth. It also has levees or deposits on the sides of it, which we'll talk about here in a minute, and eventually we'll have delta forming down toward the end. Now, when the river gets to the meandering stage, first of all, you may not see much of a valley. You look around, it looks very flat all around it. Okay, but when it goes to a flood stage, okay, when the water comes up, it's flowing pretty fast in the river bank, but once it floods over the side, it slows down, and therefore it dumps a lot of that mud and stuff. Same thing's going to happen to people's houses over here. Okay, once it gets in the house and it can't flow at all, then it's going to dump a lot of sediments. That's why you always see people talking about a foot of mud or whatever in the back of their thing after a flood. So as it jumps the banks, it automatically starts slowing down because it's not flowing down in the riverbank as much, and it dumps dirt here. Well, these become what we call natural levees, little high spots, high banks on the side of the rivers, and it helps protect it from flooding as long as it doesn't get over the levee. Once it gets over the levees, talk about the levees breaking or whatever, then you've got problems because now it's going to flood, and everything back behind it is below the level of the levee, so it's going to flood. It's particularly important in places like New Orleans and so forth, where they're actually below sea level. So if it breaks the levees, then it's going to flood everything, and so it do all the catastrophic damage that it does. It wasn't actually the main hurricane that did so much damage as much as once the seawater broke the levees and started flooding. That caused a lot of that damage. Okay, and these are natural levees. Now we can build those up with sandbags and so forth to try to make it stronger, and then that will help protect us from some of the flooding and so forth that will happen. All right, we have just a little bit left. We're not going to be able to squeeze it on this video, so we're just going to go ahead and go to the next video, and it'll be a short one. See you there.